And I would like to give you a very brief overview of the diagnostic test that can be used for arbovirus infection diagnosis. It was already mentioned by our first speaker that we are going to focus on two family of two genus of viruses now, the alpha viruses especially with chikungunya, and here the flaviviruses with Zika, dengue, and I will just give 2 words about Japanese encephalitis because it's not in our topic today. But here it is sergeant tree, I put it here to show you how closely related the dengue and the Zika virus are. And this will have an implication in terms of diagnostic. I will explain that a bit later. While Japanese encephalitis, yellow fever, and this group West Nile are a bit more distant genetically. Is my speed okay? And my accent okay? Okay, I keep it. I cannot change the accent, but I can speak slower. This is, I believe, a very important slide. As you know, there are two big family of methods, two group of methods that you can use for diagnostics. The direct methods and the indirect methods. The direct methods are the one who give the most confidence in the results, while the indirect methods are the cheapest one, the easiest one to implement, but they lack of specificity. So when you send your sample to the lab and you ask for diagnosis, you will always have to play with between these two limitations. The confidence that you can have that when you have the result, for sure it's dengue, or it's for sure it's Zika or chikungunya, and what the lab can offer and how much the patient can pay, because that's a limitation. So in the direct methods that consist at detecting the virus or its proteins or its genomes, you have a lot of confidence, while in the indirect method that consists at demonstrate the presence of the virus in the body, but not directly, but because you see the reaction of the body by producing antibodies, IgM and IgG. You have to understand when to collect specimens, because based on the timing of the specimen collection, you can do some tests and not others. So dengue viremia starts usually probably 2 days before the onset of fever, and then last for 5 to 7 days. At this time, you start to have a rise of the IgM. In primary infection, when you have the first infection with a dengue serotype, this is a bit delayed. The IgM starts a bit later. During secondary, it starts a bit earlier. But in dengue, in around 20% of the case, you may not find IgM. And we can detect then West Nile, Kujin, Murray Valley, Japanese encephalitis genome in a single tube in one test. So this will be now not an indirect method by detection of antibody that only give a suggestive result. This will give a confirming result because you detect the genome, you detect the virus itself. The NASBA, well, I will maybe not go into the detail of the technique, but basically it's a RT-PCR, but that can be conducted with only one temperature. Usually it's around 42 degrees. So with very basic lab instruments, we just, how you call bain-marie, the water, I forgot the name in English. You have that keeps the water at the one temperature where you incubate things inside. Water bath. Oh, so easy. I just went out of my mind. A water bath. So you just have the water bath, and that's all. You mixed the different enzymes and the primers corresponding to the virus that you want to detect, and that's all. At the end, you will detect the genome. So it's pretty easy. It's adaptable for to the field, and more now you can see application for people going into epidemiological investigation in the field, or go to conducting study using this simple system, which is much easier than all the PCR equipment that you need otherwise if you want to do PCR or real-time PCR. This is another one, also an isothermal amplification called LAMP. Basically, the principle is the same. You incubate only at one temperature, but you use a different approach with different primer called the looping primer, the stripping primer, in order to create a loop in your genome that will be used as a template, and with the time you get amplification at each round of here the sequence that you want to amplify. Again, it doesn't require very expensive equipment and is now more and more used in the field. You have here a paper published in 2015 showing the LAMP application for diagnostic of dengue serotype 1 to 4. They claim in this paper that it was as sensitive as the real-time PCR at that time. The microarrays, or the chips, or the DNA chips. So you use a slide here on which you will spot specific probe. So if we take the example of the chips that aim to detect different viruses for medical purposes, in each of these spots you will put one probe corresponding to one virus, one family of virus, or one species of virus. Okay? Let's say here dengue 1, dengue 2, dengue 3, dengue 4, chikungunya, Zika, Japanese encephalitis, flu A, flu B, etc. Then after reverse transcriptase or RT-PCR, you will add on the amplified genome from your sample, you will add here a label. After, you will just add your amplified product on the slide. If the amplified genome corresponds to the probe, then it will bind. And you have a laser that will detect that you have a signal, meaning that the probe find the corresponding genome of the virus. So it seems simple on the principle. It's not that much actually. And these chips are not expensive if you order like 10,000 or 50,000 of them, or if you do them yourself. It's quite cheap, but if you buy them, believe me, it's very expensive. So this can also be used to resequence a new pathogen. This has been done in the example of this paper. And this is now the last method. Your agony will end soon. I'm stopping there. Is the mass spectrometry. So I'm not sure you're familiar with the mass spectrometer. This is used in biophysics. And basically, you will expose the samples to ions, and then you will measure the ratio of ions and mass. So don't ask me to explain more than that. I don't know. But what I can tell you is, if you will first test all the pathogen that you know, and for each pathogen you will have a specific spectrum. This is Staph aureus, this is Enterococcus fecalis, you will see here E. coli, etc. So first you produce your bank of known pathogen. You test them all, and then when you have a sample and you don't know what it contains, you will process the sample and you will look where it matched with the profile of Staph aureus or with the Vibrio parahemolyticus. So because one microorganism has one specific spectrum like that. Okay? So you can do either after cultivation or no cultivation. You can first digest the bacteria, for instance, with enzyme, or you go directly, you do a nucleic amplification, and then you do the mass spectroscopy and you analyze the data by comparing the result from your sample with the results that you have in your data bank. And now I would like to show you the most powerful and cheap way of detecting new arboviruses. I found that just this week. I didn't hear of that before. Does anybody know? It's called Google. I Googled arbovirus to have a nice picture, and this came out. Does anybody know this arbovirus? It's actually a rock and roll music band from Bangladesh. So personally, I will not call my children arbovirus or my band arbovirus, but they probably don't know what it means. Only 3 seconds and 2 cents of data, and I got a new arbovirus. Okay, terima kasih.